integrals with. So, let's see. I think I did that as a warm-up. Okay. All right. So, actually, I did put that problem on there. I'd love to do that, but we don't have time for things like that. We might come back and do it one day if we end up with some time. But limits at infinity. This is an idea that you're going to need a lot in calculus. The idea is like what happens if the numbers get really, really big, or really, really big but negative, right? Really, really small, I guess. So this is going to be our key idea that we are going to talk about for this whole thing. And I don't think we did this in any in pre-calc. We just did sort of like a crash course in limits. I don't think we looked at limits as x approaches infinity. Or maybe we did. We did? Did we do Bobo Bot now?
Yeah, I remember that.
Okay, all right. You know, Coach Wood does a little bit of that too. So maybe we did. I can't remember. I've cut that way down. Yeah. All right, so now we need to know how to do this. Bobo Bot, no, I've already given it away. It's a shortcut. But we need to know how to do it with or without the shortcut. Because believe it or not, if you write Bobo Botno eats VC on the edge of your paper as your justification for a limit on the AP exam, they're definitely not gonna. I don't even know where that came from or who taught it to me. I know Coach Woods used it too, but I don't know if there's many other, teachers in the world that use that or not. It's a strange one. It's fine to write it. You can write it on the paper. It's fine. It's just you got to have actual math to back anything up. Like if you have it over to the side, they're gonna be like, oh, well, that's something that they're using. But as long as you also have the actual math, you're fine. But if you're just like 7 Bobo Botno, they're not going to give you the credit for the work on that one. Yeah. So, for this, I don't know why I'm doing that. I don't need this whenever I'm using that. I need this. Okay. All right. So, if R is positive rational number, so R is the exponent down here, and C is any real number, then the limit as x approaches infinity of c over r squared over x to the r equals 0. And the limit as x approaches in negative infinity of c over x to the r equals 0. So I want to explore this definition a little bit because understanding what that means and why it means that is really important for being able to understand the big idea here. Okay? You might be able to do the problems with some Bobo Botno later, but I need you to understand it because it's what derivatives and integrals are based on. So, if I have an equation y equals c over x to the r, right here, it tells me c is a positive. No, actually, C doesn't have to be positive. C can be any number, all right? R must be positive and rational. Rational meaning that we can't use pi there. We can't use I, anything like that. We have to have a rational number, a number that could be made into a fraction. So, although I feel like it'd still be true if we use pi. So we got, we could have a very simple case, like in this case right here.
Man, do you remember how to do your Gazandas?
No. We're doing Bobo Botno eats DC right now, though.
Oh, no. I can't spell that.
All right. Division.
I just remember he walked up to the board and today we're learning about Gazenda.
All right. Okay, back to what we were talking about. So, actually, let's even do this. I'm going to call that f of x instead of All right, so as the numbers get bigger here, so as x gets bigger, like if I put in f of 1, I could even, well, let's do f of 1. All right, I get 1. I'm just getting 1 over 1. If I do f of 2, f of 3, f of 10, f of 100. All right, so if I plug in 1 to this, it's just 1 over x right now because my top number is 1. My top number is 1. My bottom is just the x. If I plug in 1, I get 1 over 1, which is 1. Well, if I plug in 2, now I've got 1 over 2, which is 0.5, right? And what's happening here is that bottom number is getting bigger. It does not matter what your C is. I could turn my C into 100,000. Right, the top number, it doesn't matter what it is. Now, it's going to change what the graph looks like a lot. Notice I don't even see the graph anymore. The reason is because 100,000 divided by 1 is still 100,000. But notice what's happening here. The same thing is still occurring. My numbers are getting smaller. Now, it might take till I get to, a huge number. You can kind of see as I add zeros what's happening there, that we finally get close to 0. But if as my x values get bigger and bigger and bigger, it doesn't matter what number is on top, even if it's a gazillion, right? When we go to infinity, eventually that's going to go close to 0. Also, R, it says, has to be positive and rational. So why does R need to be positive? Okay, since it's on the bottom, what would it look like if I had something like 3 over x to the negative 2? What do we do with negative exponents? We can rewrite them. How could we rewrite that? This one, you're exactly right. If we have bad children, we lock them in the basement. But this house maybe does not have a basement because we're already on the bottom floor right here. So what do we need to do with those?
Put them upstairs.
Yeah, put them in the attic. Lock them in the attic would work if you can't do that mathematically speaking. So this would be 3x squared. That ruins my analogy. That's why we can't throw them outside. Although I do sometimes do that at my house. Most of y'all get outside right now. Just go play somewhere outside. But that ruins my mathematical analogy if we send somebody outside. So you would move this back up to the top and make it positive. So if you have a negative exponent in the denominator, that actually moves it back up to the top, and now you're not doing a number divided by something. You're multiplying, and that's not the same. So that's why our R has to be positive. So what we're looking at here, if we look at this first example, our properties of limits tell us that we can do the limit of these two things separately. I'm going to write it, but normally I would not. I just want to be very clear of what's happening here. So we're doing the limit as x approaches infinity of 6 minus the limit as x approaches infinity of 3 over x squared. All right. So what is the limit as x approaches infinity of 6? If we have to plug in numbers, like think about plugging in numbers that are bigger and bigger and bigger. So 10, 100, 1,000, a million. But where would you plug it in? There's nowhere to plug it in. There's no x right there. This is just a constant. So you could like try to plug it in, but there's nowhere to plug it in. So you would just keep getting 6 over and over and over. It's just a constant. So limit as x approaches infinity of any constant is just that constant. We just get 6 because you don't have a place to plug in the number. If you had 6x, it'd be different, but this is just 6. And then, think about for this part, what if we plug in numbers that are bigger and bigger and bigger? You know, if we plug in 1, we get 3 over 1 squared, which is 3. But if we plug in 10, we would get 3 over 100. if we plug in 100, we'd get 3 over 1, 2, 3, 4 zeros, 10,000 there. And we could just keep on. And what happens as the top number stays the same and that bottom number fraction gets bigger and bigger and bigger and bigger? Where value is getting smaller and smaller and smaller and smaller, right? So this is getting closer and closer and closer to 0. And so that's what this property is telling us. Anytime you have a number on top and a variable raised to a positive power on the bottom of that fraction is going to get bigger and bigger and bigger and bigger. And therefore, your value gets closer and closer and closer to 0. So 6 minus 0 gives us 6. That's our answer. Yeah, this is one of those things that, like, it's really important that you understand your fractions well. Like, for example, I'm not going to do this, but if I had 2/3 and 2/5, not going to ask my other classes which one of those is bigger. Which one is bigger, 2/3 or 2/5? 2/3 is the bigger number. Do you think everybody in the world would say 2/3 is bigger? If they understand fractions, they should. Do you think there are people out there who'd be like, oh, the bottom number's, that's a bigger number, so 2/5 is bigger? As a person who has taught math for a while now, I can tell you definitely that's the case. There are people, oh gosh, the other day, this has been a little while back, I went to Walmart and I was like getting meat from like the deli section where they slice it for you. And I think I told him that I wanted like 3/4 of a pound. So I told this guy I wanted 3/4 of a pound. And he like just had like little teeny tiny bit. And I was like, no, I want more than that. I want 3/4 of a pound. And then I realized I'm pretty sure he does not understand what 3/4 is. So then I was, well, let's try some decimals, like 0.75. Because, you know, the scale read in decimals. He was having to convert fractions to decimals. Maybe that was the problem. I left with like 1.5 pounds of meat or something because he just kept on and didn't know. But, like, I could tell. Like, I could read into that. Like, this fella.
Was he illiterate?
I have no idea. He was not mathematically literate.
That's why the double quarter pounders and the half pounder at McDonald's, because they didn't want to act as though it was like less than.
I bet you're right.
They have a double quarter pounder.
And they call it the double quarter pounder because if they called it a half a pound, people might think that it was less because they would think that 1/4 is greater than 1/2.
So that's why it's called the double quarter pounder.
Yeah. They should hire you for marketing, Liam. Everyone will think they're getting more. Let's erase that for if people think that I actually think 1/4 is greater than 1/2. But yeah, we have to make sure we're thinking about fractions correctly. And I'll admit, like, if you don't stop and think, it's easy to think 2/5 is bigger. Yeah, but we're thinking about that bottom of if the bottom of the fraction's getting bigger, that makes our value closer to 0. We're looking at 3 over 1, 3 over 10, 3 over 100, 3 over 1,000. Okay, so let's look at how we'll do these problems. Now, if you happen to remember Bobo-Botno, it is going to come into play. But I want to look at it mathematically also. So if we are doing, because there are a couple cases where we have to be able to do it mathematically and not just shortcut. Good news, there's lots of cases where you can just shortcut it. So a lot of these show up on multiple choice. You can just Bobo-Botno, put down the answer, you're good to go. Or it's a very small part of a bigger problem. Bobo-Botno, put down the answer, you're good to go. You don't have to write down Bobo-Botno. You can just give the answer. But there are some where we're going to need to think about it mathematically. So for these, what we want to do is divide every term by the highest degree variable from the denominator. It's important that it comes from the denominator. In this first one, you probably wouldn't get mixed up because x is your highest degree variable, right? So what you will do for this is you divide every term by x. It is legal to do this because that's just like multiplying the top by 1 over x and the bottom by 1 over x. Is essentially what you're doing. As long as you do it to the top and the bottom of a fraction and you're multiplying or dividing, you can do that. So what this gives us is the limit as x approaches infinity of 2x over x is just 2. And then we'll have 1 over x. And then x over x is 1 plus 1 over x. Now, it looks like we've made this more complicated, but we can use our properties of limits here, and I'm going to write it out the long way this one time just so you guys understand what's happening. When we take the limit of this using properties of limits, we're doing the limit as x approaches infinity of 2 minus the limit as x approaches infinity of 1 over x. And then we got limit as x approaches infinity of 1 plus limit as x approaches infinity of 1 over x. Okay. I never write that step, but I'm writing it now just for you guys to very clearly see what's happening. So if we do all of these limits, if we take a limit of anything, of a constant, we're just going to get that constant. And then right here's what we're looking for. This is why we divided. I have a number over x. What's going to happen to that fraction as the bottom gets bigger and bigger and bigger and bigger? 0. So we get 0 right there. And then limit as x approaches infinity of 1 is a constant. Again, we've got a fraction, number on top, variable on bottom. What happens is the bottom of that gets bigger and bigger and bigger and bigger. 0, right? So if we have a number divided by a variable to any positive power, then we're going to get 0 for that when we try that limit as x approaches infinity. So if we do this now, we just got 2 over 1, which of course is 2, and that will be our answer. Okay, questions? All right. Example 3. We've got to divide everything by the highest degree variable from the denominator. What is that going to be for this one? X squared. So we're dividing everything by x squared. And so we will have the limit as x approaches infinity of 3x over x squared. One of those x's will cancel, and I'll get 3 over x. And I'll have minus 1 over x squared. And then here, both of my x squareds will cancel right here. I'll get a 2, and then I'll get 5. 5 over x squared. And so I'm not going to write it out because it takes too long. I'm just going to take the limit of each one of these pieces. What is the limit as x approaches infinity of 3 over x? 0, because I have a number over a variable. As the bottom gets bigger and bigger and bigger, I'm going to get the value gets smaller and smaller and smaller. All right, 1 over x squared, also 0. All right, 2 is 2. 5 over x squared, 0. All right, so that gives me 0 over 2. What is 0 divided by 2? 0. So my limit for this would be 0. Okay. All right. Example 4. Okay. We would divide everything by x to the third for this one. Okay. That is going to give us the limit as x approaches infinity of 3 plus, here we'll have 2 over x then we'll have a 5, and then we'll have minus 1 over x to the third. And so if we do the limit of each piece there, constants just remain constant, so that 3 will remain 3. What is 2 over x going to be? 0. Anything with that variable on the bottom, 0. Then we have 5, and then 0. So we get 3/5. Okay. All right, example 5. Now, here's one where it becomes a little bit more important that we're actually doing this mathematically instead of just relying on Bobo-Botno, depending on what our answer choices look like. What should I divide by on this one? What? X to the second, because we're dividing by the biggest variable from the denominator. So I'm glad that you actually answered that wrong, Luke, because that's very common. That's what people do wrong on this. So thank you for pointing that out. Okay, so now this one's going to be a little bit different. We've got 2x cubed over x squared is going to be 2x. This is the first time we've seen an x left that was still in the numerator, right? That wasn't in the denominator of a fraction. So that's going to be significant, 5 over x squared over 3 plus 1 over x squared. Okay, so I've got to do the limit of each piece of this. Now, the limit as x approaches infinity of 2x, what is that going to be? Okay, that's going to be infinity, right? Because as those numbers get bigger, like if you think of plugging in 1, you'd have 2. Plug in 10, you'd have 20. Plug in 100, you'd have 200, right? Those numbers are going to get bigger and bigger and bigger and bigger and bigger without bound. So you will have infinity plus 5 over x squared. What will I get as that value approaches infinity? What? For the 5 over x squared? As x gets bigger and bigger, so we can think of like plugging in 1, a 10, 100, 1,000. You've got 5 over 1, 5 over 100, 5 over 10,000. That one's going to approach 0. So anything where you have a variable in the denominator. Huh? Okay. Sorry, I misunderstood you there. Okay. And then limit as x approaches infinity would be 3. And then what about 1 over x squared? 0. So that is going to give me infinity over 3. And it might be kind of, it's probably not great that I'm using equal signs here for infinity because you can't ever actually get there. Mathematically, this might be a little bit shaky. Most of the time, these are multiple choice anyway, so it'll be okay. All right, what is infinity divided by 3? It's still infinity because infinity overpowers everything. What is infinity divided by negative 3?
Negative.
It is negative infinity because when you divide a positive and a negative, you will get a negative. So if you divide by a negative, it can change your answer, but you're pretty much always going to get positive or negative infinity for something like this. Now, this is important because Bobo-Botno will tell you that the limit does not exist, but it will not tell you whether it's positive or negative infinity. So we have to do these mathematically to be able to tell which one it is. All right, so did I put Bobo-Botno on one of these slides later? I didn't, did I? I don't see no Bobo-Botno either. Okay, so let's just real quick, I'm going to put a new slide in right here, something over to the side. Let's review our Bobo-Botno because that's our shortcut. Bobo-Botno eats DC. All right, so anybody remember what it stands for? Bigger on bottom 0. Right. So if your rational function has a bigger exponent on the bottom numbers are going to get bigger faster. It's going to go to 0. Bigger on top, not 1. Okay. This really means limit does not exist. And it's going to be positive or negative infinity, but you're going to have to do it mathematically to decide which one of those it is. And then etc. Exponents are the same, divide coefficients. So to real quick flip back through the ones that we've done, I'll flip that up there for you guys to get it. We're going to flip back through. A lot of these can be done in an instant. On the homework, you're going to have a lot of these. You don't have to write it all out. If you can do it with Bobo-Botno, go ahead. If you can look at it and tell the answer is 1/5, write down 1/5 and go on. You don't have to do it mathematically unless you run into some of these instances where you need to do them mathematically. All right, so like if I look at the first one, exponents are the same on top and bottom. I've got x to the first, top and bottom. You're only looking at the biggest exponent because what happens is x squared is going to get bigger faster and faster and faster, and the other numbers don't even really matter much anymore. So I could look here, 2 divided by 1. 2 is my answer, right? This one is bigger on the bottom. You have x squared on the bottom, only x to the first on top, 0 will be your answer. This one, exponents are the same, x cubed in both places. You're just dividing those coefficients, 3 and 5. The other stuff out here does not matter. As long as those exponents are lower, it does not matter. What happens is when you get to really huge numbers, a gazillion to the third power is so much bigger than 1 that it doesn't matter that you're subtracting 1 because you have a gazillion cubed right here, which is huge, right? And then for number 5, you can tell just by looking, because this was bigger on top, that you are not going to have a limit there. The limit does not exist. To know whether or not it's positive or negative infinity, you actually have to work it out for that. Okay? Now, there are also some weird types of problems that we have to look at. Okay? And some of these are going to have square roots in them, and I'm pretty sure that we did not look at these in pre-cal because these are a little bit more complicated. If x approaches infinity, the square root of x squared is going to equal x. Okay, so what's going to happen here, we need to divide by the highest exponent in the denominator, but notice what we've got here. We've got an x squared, but it's underneath the square root. So when we divide by x squared here and x squared here, both of those are underneath that square root. So we're not really dividing by x squared. We wouldn't divide by x squared in the top because this stuff is underneath the square root. So what we're really dividing by up here is the square root of x squared. But for positive numbers, the square root of x squared just equals x. All right? So that would look, I'm going to write an extra step here. You don't necessarily have to write it like this. You got 3x over square root of x squared is just x minus 2 over square root of x squared is just x over square root of 2 minus 1 over x squared. And so these right here will cancel. And we are going to look at each piece like we did. So the limit as x approaches infinity of 3 is just 3. The limit as x approaches infinity of 2 over x would be 0. This stuff is going to be under the square root. A square root is like a power. It's like raising something to the 1/2 power. So you can, the properties of limits said if we have something raised to a power, we can just take our answer for the limit raised to that power. So we can take the limit inside of the square root. Limit as x approaches 2 is 2. Limit as x approaches 1 over x squared is 0. So this is going to give us 3 over square root of 2. With free response, just leave it there. You don't have to rationalize. If it's multiple choice, you might see it rationalize. It's going to be 3 root 2 over 2. That would be okay as well. Ask me that question again. Yeah, that is from unit circle. But I think it might just be coincidence here. So, I don't think there's a direct relation to those. Alright, so, now, everything I've done so far has been as x approaches infinity. Pretty sure the next one's negative. Yeah, it's negative infinity. So let's stop and talk just a minute. Does it matter whether we approach x equals infinity or negative infinity for our values? Like if I have f of x equals 1 over x, right? If I am approaching negative infinity instead, if I plug in negative numbers that are getting larger and larger and larger in magnitude, I might have 1 over negative 1, right? Then 1 over negative 10, and then 1 over negative 100, and 1 over negative 1,000. Now, I am approaching, these values are negative, but what am I still getting closer and closer and closer to? I'm getting closer and closer and closer to 0. Okay? So, for all of the first ones that we did, without square roots, I could change all of those to x approaches negative infinity. It would not change our answers. Okay? So if you are just dealing with like polynomials in a rational function, you don't have any square roots, it's just positive infinity, negative infinity, doesn't matter. You can still use blah, blah, blah for those. Doesn't matter. So the first one where it does matter is example 7. Okay? Now example 7 looks like the exact same question. But x approaches negative infinity. And with square roots, this is going to matter. Because if x approaches negative infinity, it means we are plugging in negative numbers. Okay? So I want you to think about plugging in negative numbers into the square root of x squared. Okay? If I plug in, if I do negative 3 squared and do the square root, there's a couple ways to think about that mathematically. If I square this first, I will get square root of 9, which will give me 3. If I think of it this way, negative 3 squared square root. If I think of the square root and the square canceling each other out, which is what we do a lot of times, I'll get what I put in, which is negative 3. Okay? The way that we need to think about this for these problems, because we're approaching negative infinity and we're plugging in negative numbers, the square root of x squared for negative numbers, we need to treat it like it's negative x. Okay, this is only for x approaches negative infinity. So we would do this problem in a very similar way to the last problem that we did. We would divide by x squared right here. And we would divide by square root of x squared in the top and bottom. So limit as x approaches negative infinity of, this is going to be, in this case, because x is approaching negative infinity, we need to do 3x over negative x minus 2 over negative x. Okay. In the first problem, x was approaching positive infinity, and we used positive x right there. Square root of x squared was positive x. For negative numbers, it's going to be negative x. And then here, we'll have square root 2 minus 1 over x squared. So I am going to simplify this and write out this extra step. The x's cancel here, but that's going to leave us with a negative 3 minus 2. Actually, I can make this plus 2 over x over square root of 2 minus 1 over x squared. So now, if we do the limit as x approaches negative infinity, we will get negative 3 plus 2 over x is still 0. Doesn't change anything that you have that negative infinity there. Then we'll have square root of 2 minus 0 here, and we will get negative 3 over square root of 2. Now, for most everything you're going to see, what happens is you end up with a positive and a negative. Like if you had the same problem and one approaches positive infinity and the other approaches negative infinity, you end up with a positive and negative of the same number in most cases. I'm sure there's some exceptions to that, but for what you're going to see, it's going to be the case. This only happens with square roots, so we don't have to do anything special if it's just 3x minus 2 over 2x squared minus 1. If the square root wasn't there, we'd just do it like we did the first problems. Okay, questions? Okay. Try this one right here. We're going to look at Valerius. Alright, here's what she has done. In the bottom, she divided by x squared. This is underneath the square root. She got 1 minus 3 over x, because one of those x's will cancel there. In the top, she divided by negative x. That's because of our negative infinity here. You get negative 5, 1 over x. This is going to give you negative 5 over square root of 1. What is square root of 1? 1, so we get negative 5 for our answer. You guys all right there? Makes sense? Okay, wonderful. All right, let's move on to a couple more things. And we'll be done with these. All right. Okay. Trig functions. I think this is what I was thinking of when I messed up the squeeze theorem the other day. So this is important to remember here. I must note, this is what I was thinking of for squeeze theorem. The actual squeeze theorem for x approaches 0 is like way different. And I've totally neglected that and may never think of it again until next year when I mess it up. Alright, so if I've got sine x over x, sine x right here, what's the highest value sine can be? 1. Lowest value sine can be? Negative 1. Sine is always between 1 and negative 1. If I divide everything by x, then this statement right here is also true, right? So, if I do the limit as x approaches infinity of negative 1 over x on this side, I would get 0. If I do the limit as x approaches infinity of 1 over x on this side, I would also get 0, right? So, if the limit on this side is 0 and the limit on this side is 0, that tells me the limit as x approaches infinity of sine x over x is 0. You could also use some similar reasoning for cosine x. Make sure you're keeping this straight. This is limit as x approaches infinity. What was the limit as x approaches 0 of sine x over x? That was 1. Okay, those are different things, so we don't want to interchange this. The way I usually think about this, sine x is between negative 1 and 1. That's not a big number, right? It's never going to get a lot bigger. So if we're plugging numbers in, we can treat it just like it's a 1 right there, like it's a 7 or any constant. Because that top number is just going to go back and forth between really small numbers, while the bottom number is going to be 1, 10, 100, 1,000, a gazillion, however many, right? Keeps on going up, so this is going to approach 0. Same thing would be true for cosine because it's also between negative 1 and 1. So, if we see something like this, limit as x approaches infinity of sine of 3x over x, we are going to treat this like it is a coefficient, because what's the biggest sine of 3x is ever going to be? 1. Lowest it's ever going to be? Negative 1. So as the bottom goes 1, 10, 100, 1,000, a million, a gazillion, as it gets bigger and bigger and bigger, it really doesn't matter because that top number is so little that it's going to be 0 for that. Now we can't exactly do that with 10. Because for 10, I've also got this 2x right here. If I just had the negative cosine x over x, I could just say 0 like I did on the last problem. But this one, I do have this 2x right here. So there's two ways I can think about it. I can either do what we've been doing for the other problems. I can divide everything by x. I can do limit as x approaches infinity of 2 minus cosine x over 1. And the limit as x approaches infinity of 2 is 2. What is the limit as x approaches infinity of cosine x over x? It's 0, because cosine's a little number, right? Between negative 1 and 1. X is getting bigger and bigger and bigger. So that's 0 and 1, so I get just 2 for my answer. Your other option on that, another way to think of that, because you just have a single denominator, is you could use the love connection there instead of dividing everything by x. And if you did that, you'd get 2x over x minus cosine x over x. This would cancel. You'd still get 2 minus 0, which would give you 2. I'm being lazy there on limit notation, but that's So your assignment is going to come from page 115. And let me look at it and see if it's got any E's in it like I wanted it to have. And if it doesn't, I'm going to have to do an E problem. I stopped before the E's. But I need you to be able to do an E problem. Alright, let's do... There's only one E problem here. Well, I'll show you a couple. Alright, there is one other thing I need to show you. We're going to add it right here. What about if I'm doing the limit as x approaches infinity of 2 minus 5e to the negative x? Let's send that negative exponent to the basement, because whenever things are in the numerator, it's going to make that difficult. So let's think of it this way. This is going to be 2 minus 5 over e to the x. All right, so now let's think about what's going to happen. Limit as x approaches infinity of 2 would be 2. That's just a constant. All right. What about 5 over e to the x? E to the 0 is 1. Let's think about plugging in bigger and bigger numbers. 5 over e to the first power. 5 over e to the 10th power. 5 over e to the 100th power. Okay, e is 2.71. What's going to happen as you're raising it to bigger and bigger exponents? The value is going to get closer and closer and closer to 0. So e to the x is not x raised to a variable, but it can be treated as such whenever you're dealing with this. So that is going to be just 0 there, and we'll get 2 as our answer. Now, there's one more thing about these, though. What about this? Limit as x approaches negative infinity of 4 minus e to the x over 5. Let's just go with 5. I don't want to make it too complicated. Alright, so if this were positive infinity, right, if this were positive infinity, let's look at this with both, because you're going to have a problem from your almost. 4 would be 4. What am I going to get whenever I do e to the x power? 1 over e to the x would be 0. This is just e to the x. It would be infinity, because it's just going to get bigger and bigger and bigger and bigger. I'll have e to the first, e to the 10th, e to 100th, e to a millionth, and that's going to be a huge number, right? Over 5. What is 4 minus infinity? Negative infinity over 5. What is negative infinity over 5? Negative infinity. Okay. That's how we would do this for positive. Negative is different. Negative is going to be different for this because my x is in the exponent. What happens when you have negative exponents? You're looking at like bottom of a fraction, right? What I like to do for these, if I see these with e to the x, I'm going to write it this way. Tell me if this is equivalent. Are those two statements equivalent? I changed this to a positive infinity, but I made my x negative. So if I think up here, if I plugged in negative 1, I'd have e to the negative 1. Plugged in negative 10, I'd have e to the negative 10. Let's think about this here. I'm approaching positive infinity. If I plug in 1, I'd have e to the negative 1. Plug in 10, I'd have e to the negative 10. So it's doing the same thing. So if you have one where x approaches negative infinity, you can rewrite it and make it a positive infinity and change all your x's to negatives, wherever they may be. If I do that, then this is actually limit as x approaches infinity of 4 minus 1 over e to the x over 5. So, my limit of 4 would be 4. My limit as x approaches infinity of 1 over e to the x is 0 and 5. So I'll get 4/5. So it's a much different answer with the positive and negatives there. So e's and square roots are the times that you're going to run into issues with those. Okay, questions? All right, let's see. Do a few of these problems, and then 10 minutes before class is up, we're going to go over one of those parts of the FRQ. Perhaps the x approaches infinity part, because that might be our most important one to look at.